This content is produced by PASS, the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. A ground rod in the dirt is not the fast return path that makes a circuit breaker open during an equipment fault. The critical path is the permanent, continuous, low-impedance connection through bonded metal and the equipment grounding path back toward the electrical source. If a live conductor touches a metal case, that path must carry enough fault current for the breaker or fuse to operate quickly. If the path is loose, broken, or too resistive, the metal can remain energized while the protective device stays closed. That is the central idea I want you to carry through this entire lesson. Grounding, bonding, and ground fault protection are related, but they do different jobs. As a general building contractor, I am not asking you to design a grounding electrode system or size conductors. I am asking you to recognize whether the safety path has been coordinated, protected, inspected, and kept continuous before work is concealed. Impedance is the electrical opposition that limits current flow. In field language, a low impedance path is the wide, clear route that lets fault current move fast enough to operate protection. A high impedance path is the narrow, damaged route that restricts current. The breaker does not trip merely because a metal housing has become dangerous. It trips when the fault produces enough current through a proper return path. Imagine a corded metal tool with an internal conductor that comes loose and touches the case. With an intact equipment grounding path, the case is connected through the grounding conductor and bonded metal back toward the source. Current rises sharply, and the breaker or fuse can open the circuit. Now imagine the grounding pin is missing, a connection is loose, or a metal enclosure was never bonded. The case can become the energized point, and a person touching it, while also connected to ground, can become part of the return path. I use a simple memory connection. The breaker needs a strong electrical signal that a fault has occurred. A low impedance path delivers that signal as high fault current. A weak or broken path can hide the fault from the breaker while leaving the hazard in place. Grounding and bonding are not interchangeable words. Grounding connects an electrical system to the earth through a grounding electrode. Bonding joins conductive metal parts together so they form a continuous low impedance path. Equipotential safety is the related idea of reducing dangerous voltage differences between conductive parts by connecting them together. I put the three field ideas side by side in this chart. Grounding reaches the earth. Bonding joins metal parts. The equipment grounding and bonding path gives fault current a reliable route that helps the overcurrent device operate. That last point is where many people get turned around. The soil is not a replacement for the metallic fault path. Compared with copper and properly bonded metal, earth is a poor fault current conductor. A ground rod can be part of the grounding electrode system, but driving a rod next to a faulty machine does not automatically create the low impedance path needed to trip the breaker. I want you to separate the words in your mind. Grounding is the earth connection. Bonding is the metal-to-metal continuity. Effective fault clearing depends on that continuity staying permanent and low impedance. Bonding also matters where different metal systems can be touched at the same time. Metal piping, structural steel, electrical enclosures, and other conductive parts can develop different voltages during a fault if they are not properly connected. Proper bonding reduces that dangerous difference and provides a controlled path for fault current. I would never treat this as permission to touch energized metal. It is a protective system that supports fast fault clearing, not a substitute for de-energizing and safe work practices. Temporary power deserves special attention because construction sites combine cords, damaged equipment, weather, damp surfaces, and constantly changing work areas. California rules require approved ground fault, circuit interrupter protection for 120 volt, alternating current, single phase, 15 ampere, and 20 ampere temporary receptacle outlets that are not part of the permanent wiring. A ground fault circuit interrupter watches for current, leaving the intended circuit path. When it detects an imbalance, it opens the circuit quickly. That protection is different from the equipment grounding path. The grounding path helps carry fault current. The ground fault circuit interrupter detects leakage and interrupts power. A sound job site setup can depend on both. California permits an alternative called an Assured Equipment Grounding Conductor program. This is not an informal promise that the cords look fine. It is a written program with daily visual inspections and continuity testing at intervals that do not exceed 3 months. The employer has to administer the program. If the program is not written, not documented, or not actually performed, calling it an alternative does not make the temporary receptacles compliant. The decision matrix on screen separates the main temporary power conditions. A temporary 120-volt, 15-ampere, or 20-ampere receptacle needs approved ground fault circuit interrupter protection unless it is covered by a compliant written, Assured Equipment Grounding Conductor program. A double-insulated tool can be allowed without an equipment grounding conductor when it is distinctively marked, but that tool does not erase the receptacle protection requirement. Those are separate layers. Suppose a framing crew plugs a double-insulated saw into a temporary receptacle. The two-prong plug may be proper for that tool because the tool has the required marking and internal insulation system. The receptacle still has to meet the construction site protection rule. Double insulation changes the tool grounding requirement. It does not cancel ground fault circuit interrupter protection for temporary power. The general building supervision question is practical. Before production starts, who has verified the temporary power source, the receptacle protection, the cord condition, and the inspection program if that alternative is being used? A job site habit is not the same thing as a compliant safety system. Portable generators create another common confusion. Under the California rule described in the source material, a portable generator frame does not require a separate grounding electrode when the generator supplies only cord and plug connected equipment through receptacles mounted on the generator, and the non-current carrying metal parts are bonded to the frame. That condition matters. I would not turn the generator exemption into a universal statement that generators never need grounding electrodes. The source-backed rule is narrow. It addresses a portable generator serving direct cord and plug loads from its own receptacles with the required frame bonding. A generator connected into a building electrical system is a different configuration and requires electrical trade coordination under the applicable design and inspection requirements. The generator frame is acting as the common bonded reference for the equipment connected directly to it. That does not remove temporary power protection duties. If the receptacle and job site condition require ground fault circuit interrupter protection, the fact that a ground rod is not required under the stated generator conditions does not eliminate that protection. Imagine a remote site where a crew uses a portable generator for a corded circular saw. Before relying on the no ground rod condition, I would verify that the saw is plugged directly into an onboard receptacle, that the receptacle grounding terminals and non-current carrying metal parts are bonded to the generator frame, and that the temporary receptacle protection requirement is satisfied. I would not extend the exemption to a feeder supplying a temporary panel without electrical review. A two-prong plug is not automatically a defect, and it is not automatically acceptable. The field question is whether the portable tool is distinctively marked as double-insulated. California permits a double-insulated portable tool to operate without an equipment grounding conductor, including in wet or conductive locations, when the tool is properly identified under the rule. That marking matters because the absence of a grounding pin alone does not prove that a tool has the required internal protection. If the marking is missing or unreadable, I would not assume double insulation from the plug shape. I would coordinate removal, replacement, or verification through the responsible employer and electrical safety process. I also keep the layers separate. Double insulation addresses the tool construction. Ground fault circuit interrupter protection addresses leakage on the temporary circuit. Bonding addresses conductive continuity. A single feature does not replace every other protection. Fixed equipment has its own grounding awareness points. The source material identifies exposed, non-current, carrying metal parts that could become energized in wet locations, or within 8 feet vertically or 5 feet horizontally of ground or grounded metal objects and subject to contact. Those parts must be grounded under the stated conditions. The same source also identifies metal partitions, grill work, crane tracks, and frames of non-electrically driven elevator cars as metal items that require grounding. For general building supervision, the practical move is not to calculate conductor size. It is to notice exposed metal, wet conditions, reach zones, missing bonding connections, damaged grounding pins, and work that is about to be covered. Then I bring the electrical contractor and the inspection authority into the issue before the defect disappears behind finishes. Concrete-encased electrodes, often called UFR grounds in the field, are a sequencing issue as much as an electrical issue. The grounding connection depends on reinforcing steel that remains electrically continuous before the concrete is placed. The source material identifies standard steel tie wires, exothermic welding, or other effective means of making that reinforcing steel continuous. Plastic ties can hold bars in position, but they do not create electrical continuity. That is the distinction a general building contractor has to catch. The concrete crew may see a reinforcement tying task. The electrical contractor sees an electrode connection. I have to coordinate both scopes before the concrete truck arrives. Consider a hypothetical foundation pour. The reinforcing steel is installed, the forms are ready, and the electrical contractor has not completed the concrete-encased electrode connection. If the pour proceeds, the electrode condition becomes concealed, and the intended connection may no longer be available for inspection or correction without rework. The better field decision is to stop the sequence, complete the electrical coordination, verify that the approved continuity connections are complete, and obtain the required inspection before placement. The source material also notes that hold-down bolts securing a structural steel column connected to a concrete-encased electrode may provide a connection between the building metal frame and the grounding system. That is another coordination point where structural steel, concrete, and electrical work meet. I treat the approved plans, the electrical contractor, and the inspector as the controlling sources for the actual installation. Metal water piping creates a memorable distance rule. Interior metal water piping can be used to interconnect grounding electrodes only when the connection is made within 5 feet of the point where the pipe enters the building. A clamp farther inside the structure does not satisfy that specific interconnection allowance. The practical effect is easy to understand. Downstream plumbing can change. A later repair can replace part of a metal run with cross-linked polyethylene or another non-conductive material. A grounding interconnection placed deep inside the building can then be separated from the metal pipe that reaches the earth. Keeping the interconnection within the first 5 feet of entrance limits exposure to those downstream alterations. Imagine a remodel where someone proposes attaching the grounding connection to a convenient metal sink pipe on an upper floor. The pipe may look continuous today, but the location is beyond the allowed first 5 feet from the point of entrance. I would reject that shortcut and coordinate the connection at the compliant location through the electrical contractor. The memory aid is simple. Find the entrance, then stay in the first 5 feet. Do not measure from the panel, the sink, the water heater, or the nearest convenient clamp location. The reference point is where the metal water pipe enters the building. I put a compact field checklist on screen because this topic is mostly about catching the right condition at the right time. At the foundation, I verify that the concrete-encased electrode work and reinforcing steel continuity are coordinated before the pour. At temporary power, I verify approved ground fault circuit interrupter protection or a properly administered written assured equipment grounding conductor program. At corded tools, I verify the grounding pin or the distinct double-insulated marking. At a portable generator, I verify the exact conditions before relying on the no ground rod rule. At metal water piping, I verify the grounding interconnection is within the first 5 feet of entrance. At fixed equipment and conductive building parts, I look for exposed metal that can become energized and for missing grounding or bonding connections. This is the general building contractor boundary I want to protect. I coordinate the work, recognize visible defects, protect the inspection sequence, and bring the electrical trade into conditions that need correction. I do not improvise conductor sizes, electrode layouts, generator transfer arrangements, or specialty electrical design. When I see a grounding or bonding problem, I ask 4 field questions. Is the path permanent? Is it continuous? Is it low impedance? Is the condition protected and inspected before concealment? Those questions do not replace the electrical code, approved plans, manufacturer instructions, or the authority having jurisdiction. They help me recognize when I need those controlling sources before the job moves forward. I want to close the technical lesson with one clean memory line. Grounding reaches earth. Bonding joins metal. A permanent, continuous, low-impedance path lets protective devices respond to a fault. Then add the job site layers. Temporary receptacles need approved ground fault circuit interrupter protection or a compliant, written assured equipment grounding conductor program. A portable generator can avoid a separate grounding electrode only under the stated direct cord and plug and frame bonding conditions. Double-insulated tools need the proper marking. Concrete-encased electrode work has to be coordinated before the pour. Metal water pipe interconnections stay within the first 5 feet of entrance. There is an audio practice quiz for this specific episode on grounding, bonding, and equipotential safety basics. It is audio-based. I read the questions aloud, and you answer by tapping, because I know you may be studying while driving, working, or moving between jobs. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about anything I covered. Subscribe so I can help you stay on track through every episode until you get your license. I am building this for the way you actually have to study, and I want to help you keep moving forward.